Well, after that fairly long-winded verbal description of the basic idea of the proof, we can now give the formal statement, the standard format description of the Turing algorithm that decides this particular language. Okay, so it's the usual format, and as usual, I've forgotten the final double quote. Okay, so here's the actual proof, and all two and a half squares pretty much on the proof idea. So non-trivial proof. Okay, so call the Turing machine that will decide this language. In other words, the Turing machine will accept all members of the language, all of them, and it will reject all other strings. Where the members of the language, they're strings. The angular brackets G. You can't see it. Well, here. Okay. And as usual, so the whole statement between double quotes, and the first line typically, well, not typically, it's standard. It's in standard format. First line is a description of the input tape to the Turing machine. Well, it's this. So it's a string formatted representation or encoding of a description of the grammar. So all the details of the grammar. Its substitution rules, the set of variables, the set of terminal symbols. Okay. So the Turing machine gets the grammar G. Okay. And it's now to ask whether this grammar can generate zero, whether this grammar generates zero strings. In other words, the language that this grammar generates is in fact the empty set. There's just no strings. Okay, that's the task of this Turing machine R. This algorithm. Algorithm, Turing machine, same thing. You define an algorithm to be what a Turing machine does. Okay. All right. Well, first step, we mark all the terminal. We mark all the terminal symbols, and I hope it's clear from the long-winded description I was giving earlier, previous session. The motivation for this. It's the pattern now of Sipser's pattern is pretty clear, I think, by now. He's assuming quite a high level of intelligence of the students, right? Sort of stuff. Now, for an MIT student with minimum IQ of 160, they're near genii just to get into MIT. They wouldn't have any problem with this. They're smart enough to this would be sort of obvious to them. But the average student, average master's student, is not of that caliber. Okay, so it's one of my critiques of Sipser is he doesn't explain enough to non-MIT level students. Anyway, okay, so you put markers on all your terminals. That's your first step, and then you go through this loop. Now notice indented, sort of spaces here on the left, and so this stage 2 is like an outer loop, and you're looping through this process, stage 3 if you like, this third thing, and what are you doing? Well, you're systematically looking. So you've got your rule set, all your rules, and let's number them. Say rule 1, rule 2, ... rule n, let's say, and then you go through this process as many times as you can until you've gone through all those n rules a few times, and without marking any new variables. Well, you'd have to think how many times do you need to go through it without doing anything. Once or twice. Oh, anyway. Okay, so you look at each rule, and so here's an example of one of them. So one of n of them, and you look at all the symbols on the right hand side of the rule to see if they're marked. Now, if all of them are marked and this one is not marked, well, mark it. Mark that one. Okay, and then you go on to the next rule and so on, and the same process. You check. Well, I guess that there's no point. You'd go when you're going through systematically, going through your n rules, let's say, you would check for an unmarked rule. There's no point checking a marked rule because you've already done that work. So go looking for the next unmarked variable in the rule, and that variable's on the left-hand side of your rule, unmarked. And then have a look at for that rule. Have a look at the symbols on the right-hand side of that rule, and if they're all marked, then mark what was formerly unmarked variable. Okay. Now, because that one now is marked, it may now appear as marked in the right-hand side of some other unmarked variable, and because it's now marked, maybe that was the last unmarked symbol in the right-hand side of this other variable. Well, and now that it is marked, well, that now means this other variable's, all its right-hand side symbols are now marked. So therefore, this second variable, it would get marked, and so on. So you just loop through until you just can't mark any more variables, right? You're just stuck. The rules don't allow it. So, okay, once you've done that, once you've looped through as many times as you can until there are just no more variables to be marked, right? You've done all the marking that's possible given your rule set. Then you come out of the loop and you go to stage 4, and then you test if the start symbol is marked, and if it is not marked, then your Turing machine will accept. Okay, and why is that? Well, if the start symbol is not marked, well, then you cannot generate a string. Right? It's impossible. I mean, think about why it's impossible. I've not spelled that out. I hope that's fairly obvious. Okay. All right. Now, if the start symbol, usually big S, if it is marked, then that means that you can generate strings, and therefore the language that grammar generates, L of G, is not empty, right? Because it's generated strings. And what is L of G? By definition, it's the set of all strings that the grammar generates, right? So if it generates even one string, then L of G is not empty. Okay. So if the start symbol is marked, then that means that strings can be generated, and that means that the language generated by G is not empty, and hence your Turing machine should reject, because the Turing machine is testing whether the language of G is empty. But if it is not empty, then that's not what you're trying to find. So you reject. The Turing machine rejects. Okay. All right. So that's that one done. Now we consider. Now you probably see a certain pattern occurring here. We're going through the same sequence of proofs, but this time for context-free languages or grammars, as we did before with regular languages or funded automata. Okay. So this next question you'll